right, good morning. Welcome back and well done for making it to day 3. Before we get started this morning, I wanted to kind of give a quick show of hands of what everybody is interested in. So this presentation is about volcanology, but I guess I've angled it to make it a little bit more about sources of uncertainty in InSAR and practically how to interpret about that sort of thing, rather than focusing 100% on volcanology, because that's always been a kind of minority interest for these courses. But looking around the room, I know there are already quite a few people who are volcanologists. So who's a volcanologist that I'm interested in? Ah, okay. That's actually quite a big proportion. Great. And everyone else is working on tectonics nicely. Industry applications. Okay, cool. Right, so most of the people in person are actually doing volcanology of tectonics. Good to know. Great. Okay, so I'm going to talk about sources of uncertainty in InSAR with volcanic applications. A lot of this course comes from work, some slides that we put together originally for a training talks by Pablo Gonzalez, who's now in Tenerife. And some other parts of it come from training workshops that I ran in a couple of volcano observatories. So it was kind of focused on, if you had a set of interferograms, how to interpret them, rather than details of time series processing or algorithm or anything like that. So it's more like a kind of practical guide. So I'm going to start off by talking about how to interpret interferograms, how to identify sources of noise. Like very simply, first of all, to kind of develop the experience to know when you're looking at atmosphere versus looking at something that might be interesting. And then how to prepare data for modeling in a more sort of practical way. Then I'm going to go through extracting different types of information about volcanic processes from InSAR imagery and from SAR imagery. So that'll be a little bit different in focus from some of the tectonics presentations, because instead of being 100% InSAR, we're going to look a little bit at backscatter and coherence and kind of using other parts of the data for the useful, getting useful parameters. And then we're going to have a talk by Jess on land subsidence as an alternative application, which has some things in common with applying InSAR volcanology and something different. And we've got a short exercise, which is using some of the COMET datasets and COMET tools that are online, so the Volcano portal and the subsidence portal. And then after a longer coffee break this morning, there's the Volcano practical, which is another Python Jupyter notebook. So that's the plan. Right. So to start off with, differential phase is complicated. I'm sure you've got that from all of the presentations we've had over the last couple of days already. Even with a lot of our best efforts and the best processing that we can do, a large fraction of interferograms can be dominated by decorrelation and by atmospheric signals. So one way you can try and look at that is to try and characterize the noise in different ways. So you'll have seen this before, but as a kind of reminder, the differential phase you can think of as the sum of the contributions to phase come from deformation, some contribution from also areas and uncertainties, something from atmospheric deformation, topographic error, and noise. And we're going to go through those in a little bit more detail. So starting with decorrelation, first of all, has someone talked about coherence over the last couple of days? Right. So what we're talking about here is noise due to multiple decorrelation processes that come from different origins. And you can try and estimate these in a kind of quantitative way. Normally, it's not something you worry about when you're doing processing. If it's decorrelated, you chuck it out, you can't analyze it. But sometimes it's useful to try and understand why something's decorrelated to make sense of why it appears in some parts of an interferogram. Is it persistent decorrelation that's always going to be there? Is it something that you can mitigate in some way or not? So it's expressed in terms of this gamma coherence parameter, which takes values from 0 to 1, 0 meaning that you have something that's kind of perfectly coherent. You have neighboring pixels which are very similar to each other, and 1 being that's perfectly coherent and 0 being no coherence at all, where it's essentially varies pixel by pixel with no relationship. So the first part component to this is kind of comes from thermal processor noise. That's not something that you can easily correct, so it's not something you worry about too much. Although it's the same across its scene, its impact varies according to the backscattered brightness. So the radar shadow correlation is 0, and the bright specular target might look like 1. If we look at geometric decorrelation, that's something that's proportional to perpendicular baseline. So from a practical point of view, it's more of a problem for some satellite data sets than others. Now, Sentinel-1, which is mostly what we were talking about during this workshop, has a really tight orbital tube. SRX, for example, has a very tight orbital tube. If you use Cosmos SkyMed data, that comes from a constellation of 4 different satellites, and your baselines vary really massively. So you can have some perpendicular baselines which are within meters and some which are within kilometers. So the quality of your data is then primarily dominated by this effect, which is how large your perpendicular baseline is and what proportion of the image ends up being dominated by geometric decorrelation. So essentially what this is as the baseline becomes larger, the coherent backscatter becomes, it deviates, becomes more different in a random way. So the critical baseline for this is dependent on satellite wavelengths. It's less of a problem for L-band, for longer wavelengths, than it is for C-band and for X-band, where it's the most problematic. So the other aspect to this, is volumetric decorrelation. So that's the influence of, normally we talk about it in terms of vegetation. So the degree to which the radar penetrates the forest canopy, for example, and that's again a wavelength dependent thing. And there's a whole field of people using SAR data to try and get useful biomass parameters like trunk volume in the forest, for example, stem volume, by looking at the ratios of wavelengths and looking at colorimetry. So UV versus VH returns. But for the purposes of volcanic and tectonic applications, this is generally a noise factor. And as a rule, if you have more volume scattering, so a lot of the bounce and the scatter from the backscatter happens in the forest canopy of small features, leaves and twigs and so on, and anything which is kind of on the same length scale as the radar wavelength, which for X-band is something like this, then it essentially becomes decorrelated and you can't move it. For C-band, you have some penetration, but it's deeper through the vegetation. And for L-band, sometimes most of you'll actually get returns that come from the ground underneath. So there are ways that you can try and simulate this. I've gone through the less usual contributions to coherence first. The one that you're mostly going to worry about is the temporal decorrelation. So that essentially means that it's a way of expressing how rapidly the backscattering properties of the ground surface change through time. So a piece of concrete, for example, will remain very, very stable and produce returns that don't vary all that much, and you won't have any temporal decorrelation. If you have vegetation, it will change through time. If you have a field that gets plowed, you'll have a moment in time when it all changes. If you have any sort of vegetation, the other big thing is snow cover. Some parts of the world you get decorrelation for 3 months, 5 months of the year. So we can try and characterize this again, and again it depends on factors such as the radar wavelength. But mostly we have to kind of come up with ways of mitigating it. So designing network structures that avoid the times where you have a rapid temporal decorrelation. So this is a kind of theoretical correlation value you can get at different radar wavelengths, and it essentially gives you an idea of the limitations of, NISAR eventually, ALOS at the moment, as compared to Sentinel, and what you can do with L-band that you can't see. I got an example of this, which actually comes from data from Central America. So he's put together from Costa Rica and Nicaragua. Essentially, the time span of interferer bands is comparing radar sats, C-band itself, to L-band ALOS. The time span of the interferograms that you can create varies quite a lot. With how useful they're going to be varies quite much. So you can see with L-band, you can look over a year and a half almost and have some degree of coherence, whereas with C-band, everything is kind of gone within 6 months. So it's an important consideration for processing strategy in practice. And this is an example from a volcano, getting kind of onto the topic. This is Arenal in Costa Rica. The grey there is a coherent area where it's possible to make measurement. Anything that's white is where we couldn't measure anything. What you can see there is the outline of lava flows from the 1960s and 70s. And everything else is essentially rainforest or tropical vegetation. And you can see with ALOS, you can get a little bit of coherence out in the rainforest. And with the X-band or nothing. ERS is a C-band instrument, which is a bit older, which you may never encounter unless you're doing kind of historical studies. And that's essentially limited only to lava flows itself. And that's partly because of this one you expect to perform worse than the C-band. But in fact, you get able to get better performance because the size of the pixels in the ground are smaller, which means if there are smaller scattering objects in there, they can dominate the pixel, and you actually get a slightly better result. So I've included that there as an example of how this works in practice. It's a trade-off between the different parameters. So this is the same thing expressed in a slightly different way. You've got X band, you've got squared, L band, K band, and C band. Expressed in terms of time, at y-axis, it's pixels above a particular threshold where the data becomes useful, and magnitude is perfectly clear baseline down there. You can see there's a very clear X line here. The usefulness of doing it drops off really, really fast for larger baselines. And practically why this matters is it has an impact in where we can use InSAR productively around the world. Some parts of the world are way easier to look at than others. The ideal situation for InSAR is a stable surface that remains relatively dry, not too much rainfall. So a desert, but not a desert with too much shifting sand. So the Atacama is beautiful if anyone works there. So this is a figure that we put together for a USGS report on how to use satellite remote sensing to improve volcano monitoring. So the x-axis here is a number of category A volcanoes, which for our purposes is essentially how dangerous the volcano is, which is something that we calculate on the basis of how active it is, how recently active it's been, but also how many people are exposed to hazards from that volcano, so population exposure index around the volcano. So you can see the more countries that have a higher proportion of category volcanoes in Indonesia, countries leading in these states as well. So these are the same regions from Indonesia and South America and Japan have a relatively high number of category A volcanoes, and you'd expect them to have high numbers of satellite observations of deformation and unrest. But actually, you've got these anomalies down here. So the green is deformation on this plot, pink and blue are gas emission and thermal alerts. And you can see there's anomalously low numbers of deformation detections in Indonesia, in Central America, and this is mostly Papua New Guinea down here in the Faroe Islands, which is essentially due to the inherent limitations in coherence and availability of data. Rather than anything else, it's harder to apply in these places. And that has an impact for example, volcano monitoring. Okay, so in practice, summarizing that for something that you can kind of use quickly when you're looking for second programs, you can expect high coherence over flat topography, small perpendicular baseline, and surfaces that remain stable. So bare rock, desert, no snowfall, limited vegetation, particularly urban areas. For low coherence, you expect that to occur over steep topography, when you have large perpendicular baselines. How large depends on the wavelength you're using, and in areas where you have dense, fast-growing vegetation in high latitudes. So taking the same kind of very basic approach to atmospheric contributions to phase, if you have some interferograms to look at, maybe that you've made yourself for the first time or someone else has provided with you, how do you work out if the signal that you're looking at is something you're interested in or just the atmosphere? So this is a kind of set of decision tree to help make the first judgment on that. So obviously, once you make a time series, you're going to have a much better idea, and that's your kind of best choice. But if you have an event you're interested in that happens rapidly, perhaps between the acquisition of two images 6 days or 12 days apart, you could do something like this. So first of all, you can look at in individual interferograms, you can look at the correlation between phase and topography. So for some parts of the atmospheric perturbation of phase, you have a correlation with topography for tropospheric stratified water vapor. And then you can plot two things against each other, and if you have that relationship, it can be transferred to atmosphere. For turbulent water vapor, you have correlation with deformation. Generally, there are some cases. The other thing that you can do is something like this.
The microphone is not working.
Oh, sorry. Should I pause? Or? Okay. The other possibility, I don't know, because no one had me online this whole time. At least someone said. Right. So if you have a set of interferograms, as I say, the best thing is to do is make a time series and look at how it varies we can that way. But in advance of that, we can do things like stacking, so essentially taking an average of lots of different interferograms. If something is if a deformation signal is persistent or steady through time, that will result in an improved signal to noise ratio of the signal or pairwise logic. So atmosphere in a set of interferograms sounds like an obvious point, but I think it's worth putting your head around if you are familiar with this data type. Atmosphere is associated with particular acquisition dates, and deformation, unless it's very rapid and occurs between two dates, will be associated with multiple of them. So if you have a set of interferograms with dates in common, you can apply some sort of pairwise logic and work out the signals associated with one particular acquisition that persists through them. And I think that's the kind of practical skill that's, if you're going to be looking at interferograms before the further analysis, it's worth kind of getting your head right around that, because you can spot very quickly whether something is going to be a real signal or something or an artifact. All good. Okay. Sorry to people online if you've missed things.
Yeah.
Okay. So interferograms are linear combinations of turbulent and topographically correlated noise. This signal is essentially just to show a set of synthetic interferograms. If you could divide them up into different components, and that's something that we try and do sometimes, this is more or less what they look like. So you have here a ramp due to changes in satellite position. You have a fake synthetic deformation signal down there, which is rotary source inflation. And then you have an atmospheric component, which is correlated in topography, and you can see it changes in sign epoch to epoch. And then you have your turbulent atmosphere, which looks, it's random, but it's spatially correlated. So it has a sort of predictable structure, which you can characterize by looking at the length scale of which you have this correlation. So ideally, you try and correct for some aspect of the atmospheric noise. So you can do that using atmospheric measurements or models, reanalysis data sets. You can use it using doing GPS data sets. That works quite well for parts of atmospheric features which are large in spatial scale, and in areas where you have good dense measurements of atmosphere. So again, it works better in some parts of the world than in others. You can make corrections by using empirical relationships with topography, and that's something that I know has already been covered quite a lot in this workshop. Or you can do it by filtering. But nevertheless, having done all those things, you still quite often end up with a fair amount of atmosphere in your interferograms, and it's something you have to deal with. So the other way to try and handle it is to reduce the noise during the inversion when you're modeling your data. So we would expect most observations, or any observations coming to be contaminated by noise to some extent. But typically we can treat that as random, but actually it's temporally or spatially correlated in reality. So if you have a linear problem, data noise can be taken into account using a covariance matrix. So what you're aiming to do with that is looking at mitigate a nonlinear inversion by applying a kind of Monte Carlo resampling approach. So if you want to do something like that, you can estimate the covariance matrix and then estimate the components of motion from that. So this is what covariance matrix would look like, something like this. So there's a few ways that you can do that. You can use a kind of autocorrelation function for the interferogram. You can look at spectral index power law behavior, or a covariance function, as you can see at the end. And that works well because the turbulent atmosphere is known to follow a kind of power law distribution with a simple index. So estimation of a coherence matrix, you can look something like this. You can simulate the variance coordinate variance matrix from some parameters that you can extract from the data. And that's normally the way that we, the step that we take before trying to do any sort of inversion of the data. So for short correlation lengths, something might look like this. And in a synthetic interferogram look like that, in fraction small scale spatial correlation. It implies that simulated noise is less correlated, and it kind of looks closer to Gaussian or random noise. It's not completely random because you've got some kind of length scale correlation, but closer. And for longer correlation length, you have highly spatially correlated data, which looks more like the kind of classic turbulent atmosphere you get in an interferogram. Okay, leaving that aside, another consideration in processing, and it's particularly important for volcanoes, or for anywhere with high topography, so anyone who works in Himalayas or the Andes, something like that, is uncertainties that come in from radar geometry and geocoding. So this, I'm sure, is familiar to everyone in the room already. But as a reminder, we talk about radar geometry in terms of azimuth, the travel direction of the satellite, and range, just the direction the satellite's looking in.
So the last stage of InSAR processing is geocoding, going from that geometry into X5 using coordinates, latitude and longitude. And we can lose data in this step in a few ways. So if, for example, your topography is steeper than the incidence angle of the satellite, you can have a shadow and you have a patch where there's no information at all. But for any topography, you have some sort of layover and foreshortening, which means that you have more spatially dense data on one side of the volcano on the other, and kind of counterintuitively, that's the side that faces away from where the satellite's looking from. And in terms of practical purposes, it means that if you're doing a study looking at high topography, it makes a massive difference if you've got both look directions, because you'll have slightly different spatial coverage from both of them. So there are some signals at volcanoes I've looked at you can only see in one look direction because they're located mostly on one slope. And they're essentially missed by the satellite that's looking directly at the slope itself. And the same would be true for particular landslides with particular orientations. So this is an illustration of what that looks like. You've got radar geometry from Atitlan volcano in Guatemala, and then you've got the geocoded version over there. And you can see this very bright. The bright returns are kind of squashed in the radar geometry. There's not all that much information there, where the darker side of the volcano is stretched over a much longer area. And that's less obvious when it's geocoded and returns back into its true shape. But I'm going to come back to questions after, I think. Yeah. All right, so this is a small point that I've included because I think it's a step that can make quite a big difference to interpretation of backscatter particularly. Do any of the people who work in volcanology recognize this really famous volcano? It isn't actually. It's no, but good guess, very polite. So it's a lava lake in here. It's a little vent. And the point here essentially is that when you've radiometrically calibrated the data, including a correction for the angle of the slope, you end up with a much cleaner image, and you can reduce the point out in the picture here is looking at these really bright returns on this steep topography. It can be mitigated to some extent. So if you're looking at well, volcanic topography particularly, but anything that's very steep, this is something that's a step that's worth considering. So normally we only really use the backscatter for assessing the stability of scatterers, or for matching images as a kind of early step during InSAR processing. But you can actually get quite a lot of information from SAR backscatter itself. This is an example of that. This is Fuego volcano in Guatemala. It's Edna Douala's work. She's also a COMET researcher. She's down at Bristol, so many of you may know her already. And this is one of the volcanoes she looked at during her PhD. And here you can see false color images where red represents an increase in backscatter, blue is a decrease, and yellow is unchanged. And what you can see here is a pyroclastic flow, which has gone down the flanks of Fuego volcano. There's some complexity for structure. If you look at this particularly here, you can see in some cases that there is increase in backscatter values and some it's decreased. So that depends on what the pre-existing backscatter was like, depends on the pre-existing topography, and it depends on the roughness on the length scale of the satellite itself. Okay. So moving to a slightly different example here, this is kind of a really old piece of work now, but I think it's a nice illustration for how to extract the direction, the true direction of motion, or have a guess at what the true direction of motion is from InSAR data. So essentially by combining look directions. Is that something that was covered in the tectonic practical yesterday? I imagine it was kind of mentioned because you're going to need both of them. Yes, okay. One person's nodding. Right.
Not much.
Okay, so this is kind of taking it back a step from that. This is a signal from Aaron over here in Costa Rica. You've got a kind of weird boxy square shaped fringes that's just on one flank of the volcano. And the question there that would allow you to determine whether this might be due to a deep process within the volcano itself, like a reservoir inflating, or something shallow sitting on the flank of the volcano, is working out the direction of motion. Because if it was an inflation deflation type of thing, you'd expect it. So for the people in the room, you can see my hands, you'd expect it to kind of look like this. Whereas if it was lava flow movements, it would be like that. So working out the direction relative to the slope is a kind of key way to figure out this signal. And you can do that fairly simply. So this is a much simpler version than what you'd have done in the tectonic practical yesterday. But I think it's nice because you can kind of see it quite clearly over a small area. You've got your ascending and your descending interferograms, or ract. You can see the shape of them there. And then from that, you can derive east-west motion and vertical motion. But the only way you can do that is by making an assumption. In this case, we've made the assumption. We made the assumption that north-south motion is negligible. Another good assumption in volcanic cases is sometimes that deformation is radial. And you can insert that into your into the expression at the top there in an equivalent way. And the answer here was in fact that the direction of motion of the lava flows was downslope, it was below the angle of slope, so it makes sense as a kind of a settling process associated with the 300 meters of lava that have been in place over the last 2 decades. Okay, so this is the kind of second category here. So it's about extracting information about volcanic processes with different types of SAR images. So I've given you a little taste of some of these already, but I've got some more examples that we'll talk through now. So you've got amplitude, coherence, displacement, topographic change. I think everything else in this training workshop is all focusing on this area, on fringes. Like the example we just looked at. So amplitude, right, is where we'll go to next. So that's when I say amplitude, what I really mean is the radar backscatter. This illustration here is another one from Edna's work. It's from Fuego, and you can see there the kind of real world interpretation of this strikiness in the backscatter allows you to try and reconstruct what the shape of the pyroclastic flows that go down the mountain were. And in volcanology, these are kind of important things for forecasting future hazard, and also for working out what kind of the mass balance of erupted material and eroded material on the volcano are. So in simple terms, the mean power per pixel that's received back at the satellite is an expression that looks like this. All the terms that are in grey are essentially things that don't really change all that much. Variation is very small, so we don't worry about them. And it's this sigma naught backscatter coefficient that you try and extract from this. So this is the example I already showed you from Fuego. You can see here we've got a slightly cleaned up version of the backscatter that shows the impact of the eruption itself on backscatter on one side of the volcano. So you can detect both the deposit emplacement and its alteration, and all the different drainages around the volcano that were affected. And a nice way of thinking about that is looking at these figures on the right here. You've got this is a matrix for a particularly small area of one of the channels from the volcano, where we've looked at the backscatter change for every possible combination of pairs of images, and from that you can pick out where the lahars have come down the volcano quite clearly, and Edna making a correlation with rainfall there to pull out more subtle features. So moving on to another application, this is lava flows in Hawaii. Here you can see, I think this is a nice example to kind of get your head around how this works. You can see there's a single pixel time series over there, which is backscatter values and how they vary through time. That big drop there is when the lava flow comes in and is in place. And you can see there's a gradual recovery up back to previous level, because these are lava flows that go on top of old lava flows. So essentially the characteristics of the material are the same in the scattering. And from that, works. Give that a minute. Doesn't seem to work. Okay. From that, you can essentially work out the timing of all the different lava flows covering this area. And you can do a similar sort of thing from coherence. And you can do something even better using retrieval topography from, for example, from tandem X, which I'll come to in a minute. So I won't linger on these ones too long, but this is another example which I think is nice because you can see
this is the lava lake, which I think is a feature that you identified correctly in the original program, in sorry, in the original start image, because you listed off a whole load of volcanoes that had lava lakes. Not the right one, but it's pretty comprehensive otherwise. There's only Erebus missing, I guess, on this area. So this one is using shadow of the crater wall to try and estimate the distance from the top of the crater down to the floor, which is essentially trigonometry. It works really well when you have exactly the right sort of geometry of image, and otherwise it's a little bit more challenging. But from here you can estimate the difference in the height of the down to the lava lakes, and that tells you something about the rate of supply and the volume of magma in the system at full way. So if we think about those examples are all how backscatter affects surface roughness on radar length scales. This is a different case. This is lava dome growth in St. Vincent in the Caribbean. And from that, you can actually retrieve the topography, the change in the topography itself, based on the assumption that all of the backscatter changes that you see are to do with topographic change and change in the local slope, rather than the change in backscatter, which is a bit of an assumption, but I think it's basically okay for a lava dome where you're having some material replaced by similar property material. And this is a retrieval of the topography that comes directly from the backscatter image itself. It's not the easiest way to get topography from SAR data, but the advantage of it is it doesn't require phase coherence. So you can do it even in an environment like this, where you have the growth of a lava dome and eventually an explosive eruption. And you can see the dome growing here at the bottom. Hi.
Just have a question about that.
Yeah.
Do you only really get the spatial extent, or because it's kind of still measuring like SAR is measuring distance, so can you get kind of volumetric estimates as well?
Yes, so you can get that. The idea is to retrieve the change in topography. So you make an estimation of the local slope and then make some assumptions about how smoothly that varies through space to retrieve the shape of the topography itself. So you get to back out a height from it as well. Change. And that's the results from this study. I've just put it in for interest. But essentially you can see that the lava dome grew steadily. These are different types of stuff like this, like the progress bounds and stuff like that. And through 7 these beautifully, and then suddenly it jumped over one day just before we had the big explosive eruption. Which is high. So, then estimating the density for the big classes and let's say we start a making model for example for this reason and you want to do from the location correction. But when the lava happening, the topography changes. So how that and most of the time we are using the same linear. So how this can affect the result? Yeah, so we did this all without geocoding in radar and then geocoded the results, because obviously we didn't have the topography. The reason for doing it was improving the topography, so we didn't have the topography in that direction to geocode it. So that was at the end of the presentation only, and only where we thought we had it. So actually there were 2 digital original produced that we used in this case. So one was pre-existing, that was before the lava dome was there. And one that was produced from structure from motion imaging aerial photography during the eruption itself. So of course you don't get anything like one of the fine sets that we used. Yeah, it's a good question. Right, I'll move on to coherence. It's near time. So coherence was the first thing I mentioned when we were discussing noise. In terms of volcanic processes, it's a neat way to map out lava flows and to map out surface changes. Here's another example from Hawaii, because great data comes from Hawaii. And you can see the lava flows in East Rift, and they're all in black, where the recent flows are, and in white, where the older flows are, which are more recent. So finally, topographic change. So this, I think, is a very exciting area in SAR volcanology at the moment, because of the anticipated launch of the Harmony mission, which is going to have time-stepped data that allow you to retrieve topography and allow you to look at a lot more cases. But what's been done in this field is already very exciting. So this example here is from Reventador in Ecuador.
And you can see that it's got the shape of lava flows down there in red coming down from the dome. And also alteration of the volcano summit itself in red and blue. So ideally what you want to get at topography from InSAR data is a bistatic mission. So where you have acquisitions from different geometries acquired at the same time. The nice thing about that is that the atmosphere will be fairly similar, and you can maximize or optimize rather the satellite separation for getting at topographic information. So I don't know if you've come across the SRTM data set for topography. That's the method used to produce that. So this is a retrieval. So this, the point I want to make with this figure here is we've got completely incoherent information here over the fresh lava flow, and what coherent phase on either side. The top of the coherence is not that the edge of the lava flow, that really clearly, and you can get topographic change if you have bistatic images that cover the same area. I think it produces a pretty neat result. This is a different example from Iceland, particularly beautiful. You can see the cauldrons in the glacier there. So you've got the large kind of blue area there is the fact called ice cap. There are melting cauldrons on the surface. You have the graben forming with the great opening, and then you have the fresh lava field, just from the bottom of the arch. You can go a little bit. I wouldn't say it's not further. I mean, it's for data sets that are not bistatic, but just sets of interferograms that were kind of more designed for looking at deformation change rather than topography. You can still do something to try and retrieve topography if you have a large data set and if you have a good distribution of baselines, essentially by solving for the relationship between perpendicular baseline and phase, and getting the gradient of that relationship and using that to assess what the baseline is. I mean, that works quite well for data sets with large perpendicular baselines. It's obviously not the optimal way to do it, but it's something that is kind of routinely done as a correction in any sort of InSAR processing flow, and sometimes there's useful information in that. So this example is Sancho volcano in Guatemala. Okay, so I've got information about the practical here, but I think I'm going to hand over to Jess, if that's okay, to talk about land subsidence, and then we'll come back to the portal stuff. Oh yeah, questions. Which method is most suitable to correct APS filtering using empirical relations on models such as GAFOS? And which component? Okay, so there's a question about atmospheric corrections, and it's quite a general one. It's what method is most suitable, and the answer is that depends on your data. There's not a kind of general answer. If you've got ERA 5, or you've got good quality ECMWF results in that particular area, then that can work very well. But I think the strategy is normally to try different corrections and have a good way of evaluating how they perform. So you know whether it's increasing the level of noise in your data or decreasing the level of noise, or whether it's introducing off. Just how well these things work depends on the type of atmospheric phase delays you've got, whether it's mostly turbulent, whether it's mostly kind of large scale stratified features. The other factor is, particularly for volcanic case studies, is that you quite often have orographic induced turbulence, which is low spatial scale and produces atmospheric features which were not going to be correctable using large scale weather models. The same thing with empirical correction, which is based on topography. The degree to which that works depends on the degree to which you can characterize that relationship from your data set, and also how widespread that relationship actually is across your image. So sorry, it's not a clear answer, but basically it depends. And I think the strategy is to try lots of things and then have a good way of evaluating how they perform. Which component, horizontal or vertical? So you'd make the corrections in the satellite line of sight rather than horizontal or vertical. It would be an azimuth correction. You want to estimate the contributions to phase from the atmosphere along, the zenith line of sight. Regarding the down use of topographic correction and geocoding, does you enhance the spatial confinement supplements? Yes, so there's a question here about whether the resolution, using a higher resolution DEM than the inherent resolution of the SAR image helps with the processing. And the answer is that it can, but what you basically don't want to do is use a lower resolution DEM, because that can significantly degrade the quality of your processing. And for if you're using X-band data at all, the quality of the results you get depends really strongly on how good the demo is. Particularly if we're looking at spotlight mode data where you have pixels by 1 by 2 meters or something like that, then you really want to have a high quality demo to get the most out of your data. For Sentinel-1 processing, I think having a digital elevation model which has roughly the same pixel size that you're in or works perfectly fine in most cases.
Yes.
Any more questions from the room? I think you kind of did them as we went along. All right, great. You're up, Jess. Thank you. Stop that. I just see slides. So I can see them. Okay. My question.
Yeah.
So. So I'm Jess, I'm a PhD student here at Leeds. Which one's the right one?
Yeah.
That one?
Yeah, yes.
Perfect. And I've been working with all these people to do work on that stream, including Susie. So yeah, let me give you questions as we go along. So it'll be a little bit less technical than what Susie's just presented, but a bit more application focused. So we'll start by talking about what land surface substance is, and I'll talk about it, where you find it, how you can image it using COMET InSAR, a bit about velocity decomposition, which you asked about before. One of the errors that people talk about when looking at this phenomenon, phase bias, and then if we've got time, some general application of what we can do with this data. So then we're interested in land surface substance, such as what we see here. Yeah? No, if not, that's fine. It's interesting anyway. And critical because it focuses on one of the important natural resources, water, fresh water, which we all need, I'm pretty sure. So here's an example of a schematic from New York Times about what happened in Mexico City. You can see by volcanic soil, that's probably focusing on Mexico City, but I focus on land. It's the same context and principle, just be different aquifer sediments. So we need fresh water for agriculture, industry, drinking, things like that. And lots of that is stored in underground aquifers. And it's a particularly good resource if you don't have many freshwater lakes or reservoirs, and this aquifer resource can be depleted. And this results in the land surface moving down, as you can see here, and that can cause, as you can see in the buildings at the top, damage to infrastructure. More detail, how does this work? So we think of this effective stress concept, which is a simple sort of equation from 1936. There's more complicated versions of this, but to think about this quite simply, we can consider water pressure. That's the pressure caused by fresh water within the aquifer's sediments, plus the effective stress. So the stress caused by the sedimentary grains within the aquifer. They support the total vertical stress, so the load that's acting upon the aquifer, so the buildings, the sediments above it. But if we decrease the core water pressure, because we're lowering that groundwater surface, the effective stress must increase. So the stress on the grains within the aquifer increases, which can cause them here, as you can see in the swallow layer, to deform and compress. The pore space can become compressed as well. And that causes what we call sort of sediment consolidation. That can cause land deformation at the surface, which we can see with satellites. And we can take this line of sight direction from those satellites to deformation in the line of sight. We convert that into more intuitive components of deformation, vertical and east-west, for example. And why can land substance be a problem? So here's a quick example. So this is an area in Iran, so near the city of Rafsanjani here in central Iran. And on top of this optical image here is some vertical InSAR data, so showing how fast the ground's moving up and down. I think it is Sentinel-1 data, so similar to the COMET data as well. Down here in the south west, you can see it's quite stable, there's no ground motion, but in the northeast, the land surface is moving down quite fast, so 30 centimeters a year. That means there's a really, really steep gradient of velocity going diagonally across the scene. And you can see perpendicular to that gradient,
we have these cuts on both. You might be able to see them here, but they're pointed out by these arrows. And that's caused by the steep velocity gradient. And these in the environment look like long linear features, long crack features, which isn't really a problem here because there's not many buildings. But this, as you can imagine, can cause damage to buildings or infrastructure if they were on top. Such as here in China, there's quite a lot of severe land subsidence in parts of China as well. And this can cause damage to buildings such as you see here. We can more quantitatively estimate these velocities of the vertical gradient by a parameter called angular distortion, so beta, sometimes referred to. And how we estimate this beta is quite a simple parameter. You just estimate the change in the vertical velocity over distance and divide that by distance. So it's just sort of measures a gradient in space. And you can, depending on parameter value of beta, there's pre-existing categories of this angular distortion in literature, so low, medium, high, very high, from engineering literature really. So you can begin to classify what the subsidence gradient is and how severe that is, what damage that could cause to buildings and infrastructure. So here we have about 30 centimeters subsidence gradient over about, I don't know what centimeters, 80,000 centimeters. So we have the medium level of angular distortion. So it's quite severe. So going back to a more global scale, where do we see land subsidence? So this was a nice study in 2021 looking at the probability of potential global subsidence based on things like geology, topographic slope, climate indices. And we can see that, so the yellow, orange, and red areas are where you're most likely to get subsidence based on these parameters. We sort of concentrate in this 30 degrees north latitude belt. And that's based probably mostly on climate, but also sedimentary features. And if you look at where subsidence is identified, this isn't completely up to date, but up to date. You can see again we have the observations where this values are predicted. So some hotspots of subsidence around the world include Tehran in Iran, which I'm interested in, Shandong in China, which we mentioned. Indonesia suffers severe land subsidence, and some more famous events in Mexico City, in San Joaquin Valley in California. So moving on to the work that I do. So my work in my PhD focuses mainly on Iran, and I've identified about 113 or 108, I think, some areas of subsidence around Iran. And these pop out really severely when you look at the InSAR data. So blue filter here is moving down really fast. So peak rates of vertical velocities, as we saw before, about 30 centimeters a year. And red reef areas moving up. Any areas moving up much slower than those moving down. And we've identified these in existing velocity fields, which is for looking at tectonic motion by Watson et al. These are all the vertical velocities, and you can find the line of sight velocities on the COMET LiCS Portal, which we'll explore in practical. And you can look at the regions that are on there at the moment, and we have region pages basically up on the right. And you can look at frames, you can look at correcting for atmospheric noise, and you can look at using filtered or unfiltered data based on the spatial temporal filter, which you might have talked about yesterday in practical. Yes, I won't talk about it. So we're seeing decomposition. This is sort of a rough work of what I do based on previous work by Watson and Payne. You can find children's papers here, and the GitHub to this velocity decomposition. I can talk about this briefly, that'd be useful. No? Cool. So how you approach this, you firstly take outputs from LiCS path, so velocity, the LiCS vectors, which you mentioned, and the velocity mass, and you read grids. So this is all done within this GitHub program here. The program regrids all these inputs into a common grid. So I think it bases the grid and the courses velocity of the inputs. So that for me is usually about 100 meters. And you can then merge these velocity and VSD, so the standard deviation velocity, that's what this is, along tracks. So you end up with these long north-south tracks of velocity and VSD. You collect this reference frame effect or segmentation effect. So this is a bit confusing to get around, we've heard it before. It's basically correcting for the motion of tectonic plates during the whole time series period. So, for example, if you're putting the east-west or north-south, you get sort of a ramp going across your big long track that you've created, and once you've measured along that, for example, like here. And you can model that page motion and correct it in this step. You can then tie your line of sight merge velocities with GNSS fields to put it in the right place in space, but also to make the problem not underdetermined, but solvable. So here we have, for example, two inputs, ascending and descending velocities, but we want to solve for three unknowns: the current velocities, east, west, north, south, and up, down. And that's not possible. But to then make that equation solvable, you insert an interpolated north GNSS field. So take the northern velocities, interpolate them in space, and insert that into your equation. So you can solve this equation at the bottom. Also, the north GNSS field is a lot coarser in space than the south velocities. So that's something to bear in mind. Yeah, you form the velocity composition. And this is sort of the results we get for a round. The vertical ones you've already seen, the east-west ones on the right. Looking a bit more detail at this rough sand I'm using here, which is in central around. You can see there's quite a lot of detail in the meter velocity as you get at the end. So this is the vertical, blue is going down, and this is the east-west. So blue is moving to the west, to the east. So you can see that there's quite a lot of heterogeneity in space in the vertical as well as east-west, and really nice patterns of where the east-west split sign. This might be caused by different sedimentary layers in the at depth. It might be caused by structural features, faults, such as that one you see here. The stripe of these switches the east-west follow the stripe of the faults as well. Or it might be some of it a residual error caused by our really coarse smooth GNSS field. So there might be some cross-half motion we're not accounting for that makes into these horizontal velocities. Looking at sort of the land use of these substance areas, you see on the top right, most of the area inside the white line, which is where the substance is agriculture. In fact, above the whole of Iran, about 78% of land substance that is quite fast with related to farmland. So moving on to talk about phase bias. Has anyone heard of phase bias? Has anyone talked about it in the course so far? Briefly. Okay, we're talking amazing detail. But it's something people are concerned about with land substance because reasons I'll talk about in a second. So what it is in a nutshell is a non-zero term added to phase difference calculated in short baseline interprogram networks, which is basically often what essential one interprogram networks are. So if we have this image, for example, essential one imaging substance, so one substance here, what is the change in phase? We have phase bias. Imagine it as imaging an ultraviolet phase at the bottom, which isn't real. And there's been several solutions which we might have talked about actually earlier. So, for example, this is a nice study that sort of works in the same area in Sicily, but changes the network structure. And areas with shorter temporal baseline have this higher value of phase bias. There's been longer temporal baselines, which have less phase bias. In subsiding regions, they're vegetated, such as in Iran, which is shown with agricultural use. So you often want to use a shorter temporal baseline interferograms to reduce coherence loss. So coherence will change less if you have shorter temporal baselines. So you want to use those, but maybe that will introduce phase bias. So that's a conflict you have to resolve when you're working on this sort of problem. As well, studies by Mercedes, so Yasser spoke to yesterday. He studied this area in Turkey, and this is a measure of phase bias in the y-axis. And we found that areas of cropland, for example, have the highest values of phase bias. So these two studies show that areas of substance with vegetated cropland are most totally susceptible to phase and signal phase bias error. So to investigate this, we looked at this area in northern Iran, which of course most of this SM1 phone, and it had been contained about 2 or 3 substance areas that you see here. So these are subsiding to like 60 millimeters a year, quite fast. So this is the original velocity, and then this is the estimated phase bias by, yes, so based on method in this paper here on the right, basically estimating the phase misclosure of the InSAR phase signal. And we remove that estimated phase file from the signal, we get this slightly cleaned up version, which looks actually quite similar to original velocities. And we find, in fact, despite expecting quite a lot of phase bias, we don't get too much compared to the actual velocities that we're estimating. So the maximum phase bias magnitude in the whole scene was sort of plus or minus 10 millimeters a year. But we're dealing with a signal that's quite fast, so 50, 60 millimeters a year, not too much of a problem. In fact, as well, within the substance region, median phase bias is only about 2.8 millimeters a year. So we have a large signal that's not too much of a problem. But something to consider if you're looking at slower signals. Yes. I have a couple minutes. I think it goes.
Yeah, so I know from astronomy that the bias usually it's like an instrumental effect in some of the things on that's what I say. So here, where is the bias coming from? The instrumental effect it is dependent on the length of it. So,
So that's what I should have mentioned. So it's a real active area of research. So that's one thing to bear in mind. So it hasn't really been researched that much potentially since 2021, 2018, because that's when people started making these long networks of short wavelength programs from central line imaging. And the debate as to what caused it. Some say soil moisture, some say scattering of vegetation, like the radar signal by vegetation in trees, like Susi mentioned, maybe a combination of both. I think that makes it difficult to research, would you say?
Yes, I think it's not completely understood.
Yeah,
where exactly that's coming from, but it's anything that introduces a bias in the same direction, which is a lot of short-term experiments. I think when people started making these networks, it's short temporal baseline networks and something like that. It's quite different how large it was. And a lot of people have used. There's lots of studies that do it, so much that I think it's probably not 100% that. So we can ask the question.
okay, so everyone say short and go there and that like say the small period.
It's a really good question. I haven't seen that anyone's actually made that estimate. Because at the moment, I think the only way is in the contract and it's just one of like actually it's part of a network. But it would be an interesting sense back in the topic.
yeah, it's not amazing. But people always ask about it when you look at non-substance.
But I can say that it only something that is not the interested. You have to it's not a problem.
Yeah. Well, I think I'll stop then. I hope that gives you a nice idea of non-substance. And we're going to practical. So would you like to go back to the sun?
Yeah, so is it what time is it? 1 o'clock? Yeah. Well, should we take a 10-minute break? So we can have a glass of water.
Yeah.
Yeah, and then
So if anyone's got any questions, let's stop for someone. So we can take this. Yeah, I'll stop anything.
Yeah, mine. It's like you said about using the UBS to calculate the node. Like just the interest how dense is the GPS, what looking at and the access you have to it.
Yeah, that's a good question. Places like one getting access to DNSS is always difficult, especially update data. The network isn't that dense. It's talking about department, but it was quite dense around, for example, Tehran, the capital where people are interested in corporate stations there. Of course, the rest of the country is more sparse. Just the nature of it. Places like Afghanistan don't have access to any DNSS data. And you get access to it. So there's a paper from 2019, which I put up there, which has lots of velocities, DNSS velocities published. But in recent fiscal times, I think there's many publications. So you just have to assume it's constant over time, these northern southern rates, I guess.
Do not call them the sliding thing
Oh yeah, groundwater depletion for sure. Yeah, mainly agriculture. Yeah, and that's quite well known. There's been a few papers on it, but it's not very active research. People think about California when they think of this problem, but it's a much more severe problem in arid areas in sort of Central Asia, I think. And then there's some online. So. Okay, yeah. So it's talking about. Okay, is this a speaker? Oh, okay. So there's a question about how to use longer temporal baselines which will decorrelate or shorter ones which use phase bias. I guess that's the whole problem. There's not a good solution.
So Pedro's the person to answer that.
Yeah.
We try to tested to increase the longest interference. We tested between increase 6 months, 9 months, 1 year interference between and mixed with shorter baselines to try to avoid this phase bias, and then we try to compare with the GPS, that is a local measurement in the ground. And we found that in the case of volcanoes in Ecuador is a good idea to use more than 12 days interference time in the time span to create more than 12 days is the answer for volcanoes in Ecuador. We tested and compared with the GPS.
And I think it's probably fair to say it's also kind of, it depends. Because as Jess says, you've got absolutely massive subsidence signals and it's just like 1 or 2%.
Yeah.
But the volcanic signals tend to be more subtle than that, and then you have to worry about whether you get it right.
Exactly.
And then there are, as Jess mentioned, methods for mitigating it apart from the condenser
Yeah,
networks.
I think, yeah, you can try to mitigate it. But as you say, it's difficult to do that if you don't know what's causing it as well. So, an active area of research. I think that's all the questions for now.
Okay, great. Well, let's take 10 minutes. I'm happy to take questions immediately in the end. Very nice.
They're from like society.
Yes, quite bad. So the question, like, what's the smallest deformation you've measured? Yeah. Okay, let's pick it up again. So the next section is essentially a chance for you to have a play with two of the COMET portals, so the Volcano deformation portal and the subsidence portal. And there are some worksheets that Jessica's very kindly got for everybody to play around. If you're online, the files are available to download from, or we post them in the chat.
Yeah,
Okay. Pedro's going to post them in the Zoom. Once everybody's got those in front of them, we can start with the exercise. So basically, what a choice. We can do volcanoes or subsidence or those. Yes, we'll have everyone, everything, everyone. Yeah, it's not really clean. It's not. It's a little about just going online. No.
Is there anything to fill in on the sheets or is it?
There's a little bit, not really. There's a kind bit, but we. I mean, it's part of next. Yeah, you can get on to the yeah. Yes.
One, two, three. Oh,
Yeah.
Sorry, guys. Spoiler. Your character.
No, you got.
Online can download for this link, please. It's not possible to send the file in the chat.
Also,
Yes. Yeah, yeah.
Right.
Yeah.
So there's a link up on the screen just now that you can use to download practical for people online if you've not found it. Did the link work, Sejin?
Yeah, it works.
Okay.
Yeah.
So the aim of the portal that these tracking is based on is essentially to make the definition data a bit more accessible. So there's a few online tools that allow you to play with it a bit, just kind of get your head around what the steps look like. So it's not for kind of detailed like research analysis of the results necessarily, more just for a quick look. So I'll start by introducing the more detail, and then you can have a play that makes some examples of things that you can try out, things like practical, just to give you an idea of what you can try and potentially do it. And then Jess will introduce substance later as well. I think we should probably leave a link. Is the link in the chat or someone can find it?
On the chat.
Oh.
Maybe then.
Okay, well, the link is going to stay up on the screen just for another minute or so. If anyone online still needs to get access to practical. If you need more time, stick something in the questions, please. The data that's available in both of these portals is the result of the LiCS automatic processing. They're selected to be useful for particular applications. So the volcanic one, it's been put to the volcanic areas around the world. There's two kind of versions of this portal available. So one is the kind of open one that we're looking at this now. If you're interested in playing it with it a little bit more after the workshop, then you can ask for a login, use your login, and then you can have access to all of the volcanoes, including ones that haven't been kind of quality checked, and you can see what your processing looks like. So the first thing you might want to do with this is have a look at the front page. We've got an index, which allows you to select volcanoes by name or by geographic region. And then on each of those, you have a bunch of tools. Okay, so I'll go back to the slides now. That's oh, it's very confusing. No. Found it. Well, I guess you've made that look easy. Thank you. Opposite way to what you think on the keyboard. Okay. Right. So the things that you can do on the portal are interrogate individual interferograms. There's a sliding tool that allows you to just click through the whole list of interferograms that we have for a particular area and see what they look like. You can construct a time series and look at profiles, spatial profiles cut across the data. Now that's particularly useful for doing the sort of thing that I started off this morning's presentation talking about. So looking at the shape of the signal relative to topography and looking at the temporal development of the signal to distinguish between atmospheric and deformation processes. And finally, there's a couple of machine learning tools on there. So one is based on CNN. It's from the Bristol group from Clee. And her work has a kind of flagging tool which pulls out any interferograms that look like they have deformation in them. There's also a tool on there from Matt Gaddis that she's been introducing this afternoon's practical. So these numbers are the out of date now. We've actually got processing for most of the volcanoes in the world. The restricted subset that I mentioned in the portal still looks something like this. There's a bit more on here now than in this slide. But if you have a favorite volcano, check out if it's on this list first and have a look on the portal.
If you have one that isn't on there, let me know and we can see about kind of adding it sooner, having a look, or I can potentially log you in. So the priorities for the processing are essentially how hazardous we think the volcano is and which volcanoes are being actively researched or in a state of eruption activity. But I mean, as I introduced at the beginning of this morning's presentation, there are some parts of the world where doing InSAR is beautiful, it's straightforward, and you get very clear results. And in others where it's much more challenging and it requires much more kind of intervention and detailed processing to make sense of it. So I'm going to kind of introduce the potential of what you can do with the portal now, based on the basis of the discussions of noise and some understanding where signals come from this morning. So you can start off by saying, asking questions like, is the signal independent of topography? If it is independent of topography, it's more likely to be deformation. If it isn't, you can see whether it's always topographic signals in this area or whether it varies. And then you can use pairwise logic. You can see if it's a signal that's associated with more than one acquisition, and is it clear in multiple hip directions, or do you only see it in ascending and descending? And none of those by themselves mean it definitely is or definitely isn't a volcanic signal, but it's a good place to start in terms of understanding what it is. And answering those sorts of questions is one of the things you can do with the tools on the portal. So you can make a profile of process and see how it compares to the underlying topography. You can use the kind of slider to look through lots of acquisitions and see if it persistently appears. And you can change, I'll show you in a minute how to do it, but you can change between different tracks to see whether the signals are ascending or not. Once you've done that, you can use the time series tool to look into a bit more detail. Are there any potential signals in there? So if there are, you need to then think about to what extent they're likely to be atmospheric and to what extent they're likely to be deformation. And you can look at that you can do that by looking at the temporal shape of the signal, but also the spatial pattern in each case. So the other things that you can do on the portal are examine the shape of the signal. We said you can look for seasonal trends. You can do some filtering. So the spatial temporal filtering here. So the red is unfiltered, the blue is filtered, so you can get something much cleaner. And in this example here, it just basically pulls out a very clear seasonal pattern, as well as a long-term trend. The other thing that you can do is change the points that you're plotting. You've got a tool to switch between displacement and coherence in this map here, and you can select either point to plot or the reference area. So the reference area is if you're plotting InSAR data, it's one of the things you have to get your head around quite quickly because it makes a big difference to what a time series looks like. And a really kind of classic thing to do when you first start looking at data is start interrogating an apparent signal in a point, which may actually be associated with the reference signal, which is kind of subtracted from reference pixel, which is subtracted from it rather than the location you think it is. So you really want to make sure that all of your images are referenced to somewhere that's stable and not changing through time, and particularly not having a kind of temporally structured pattern. And some places that's harder than others. And finally, you can also look at the correlation between the signal and line product. So in this case, you have a apparent displacement signal, which is correlated with the kind of their topography associated with the signal in there. And you can do that by flicking between the displacement and the Sentinel-2 imagery of the same area. So this is a piece of Pedro's work. So Pedro has written a paper about Sangay volcano, and he spent a long time really optimizing the processing for this volcano. And this example is, I've kind of put this in here because although I think the results from the portal, I think are really nice for a quick look, and they give you a really good impression overview of what the data are like. And in some parts of the world, that's good enough. In a lot of volcanoes, it's not, and it actually takes an awful lot more effort to try and really test the quality of the data, account for things like phase bias by improving the network or making some corrections, making tailored atmospheric corrections, using a different digital elevation model for your georeferencing and that sort of thing. But Sangay is one of the examples that's on the portal, and you can have a look there. It's a very limited area of coherence. It's a very active volcano in Ecuador. It has very regular explosive eruptions that cause incoherence around the summit. There's rainforest further down, so you really have a very narrow area of coherence, which makes it especially challenging to interpret. So if you want to look at a hard example, that's one to check out on the portal. And And one of the results from this is that I think the person who asked about fading signal is actually not here now, but I'll answer the question anyway. One of the examples here is that when you remove the experiments less than 12 days, essentially removes the part of the signal that we thought was fading and not genuinely associated with chemical process. So I won't necessarily go into these, but the other thing that you might want to look at on this example and others on the portal is looking at cross sections through different angles across the volcano to see if you can identify things such as radially symmetric and might be magmatic, and also processes that might be related to, for example, flank stability. In this case here, you've got some parts of the signal which are moving down slope. And although you can't necessarily do get your east-west and your up-down components of motion with the portal tools yet, you can get an impression of what these signals might look like by just making profiles across the volcano. So when you find an example that you want to focus on, it's another thing to check out. Right, that's for the practical. That's for the practical afterwards. Jess, do you want to talk about the substance one, and then I'll bring the website up. Yes, the substance portal is not as complex as the Volcano one, but it looks very similar. So it's got the same idea with looking at time series and profiles of information. There's no machine learning element to it. Structure will be very similar to what Susie just discussed. You can use the same tools. And lots of the ideas are quite similar and can go through worksheets. But yeah, with the substance work as well, you only get substance really in sort of topographic flat valleys, so you don't get a lot of the topographic that Susie was talking about as well. But you can see, it's interesting to see where the deformation is compared to topography to really see that the maximum substance is within the valley floors where the thick actual sediments are. Enjoy. Oh yeah, and it's also mainly focused only on Iran at the moment and the translation. So we're going to be Farsi. But we hope to expand it maybe to Afghanistan and Pakistan in the future. There's a form of feedback at the end actually, I think as well for the volcanic one. It'd be really nice to hear your feedback from both portals. Great, thanks. So I think what we'll do now is we'll just open up the portal online and yeah.
The LiCS web page, this the volcano.
Because there's some research going on and to it helps with the inside outside of experience. And a lot of comments focus
Okay. So someone just asked which volcano is used in this practical. The answer is you can choose one of your own. There's Eliot Eaton in Ethiopia is the one that's actually used to illustrate the different functionalities of the portal that you should feel free to just explore yourself. And yeah, the tools are the same everywhere.
I've done lots of work with this thing was beautiful results. It was very good information for the Well, the other thing is if you want to play games about the eruption, you can look at the information and try and see when it's erupted. In this part of the world, that's
stretch, obviously. And then you can see the displacements. Um, And this displacement signal, I think, is actually kind of quite central on the caldera, of course, because it's in the look direction, it looks like it's offset, which is a kind of common experience with InSAR. Is this assembly?
Yes.
Yes. Depends where in the time series we're looking. Yeah. It's had a really long period of inflation. Yeah. It's not for me. No. Volcano, you're interested in the data aren't there. First of all, try another track and see the process a little bit more complete, or we can hear it a little bit nicer. And this is quite a nice, rich example here, because we've had, in the period of the time series, we've had multiple eruptions. We've had intrusions that seem to have taken place underneath the caldera, but also on the flank. And there's an interesting sort of feature right down where Pedro's put the reference in, the red box, which is, it looks like a sill which extended offshore at some point. So I guess we're about the time that you're scheduled to end this session. So it's up to you whether you'd like to spend a little bit more time working through the practicals, or have any questions, or just want to sit and play with the pause for bit and ask questions while we're here. I'm around until the next session. The volcano modeling at 11. Thank you everybody for listening in and for coming in person. And thank you, Pedro, for making everything work. Yeah.
Very online people for the sound. We try to solve the problem, and we have a break for half an hour.
Yeah, 20 minutes.
20 minutes. With the volcano practical.
So trying, did it work? Do you hear me well? What about now? Now I'm quite far, but still, do you still hear me? Flash out. It's, yeah. Let's see. Hope it will work fine.
Milan.
You good? Yeah, there are
Who's
various. Sorry?
Who's leading the practical?
Good.
Okay.
Isn't it Eliot? I think. Yeah. Or Jess. You know how to hide that panel? Oh, hide load and meeting control?
Yeah.
Oh, yeah.
Yeah, but you need to start the recording.
Oh, it's not, yeah? Oh, I think it is.
Pause.
Is it? No, no, it was recording all the
Yeah.
time. I'll have to clip it afterwards, no problem. Okay.
But then realize I'm like breakfast, that's like goes twice. There's like 3 sandwiches. Well, yeah, but it's either that or like, I don't know, have be solved, I think. Yeah, 6 p a day. Yeah. That's their unknown speeds. So, just on the half model, you're obviously. Like, why is? It's all about that. Okay. I think this seven.
It's fine. Like if you go. How many people would that now? Which one's declining population statement? Basic stats. Census data including. Oh, no, it's quite tiny. So I'm sort of falling apart. That's crazy. That's
Interesting.
I got half the size of my closest. Yeah. It's weird to think my town. Yeah, is that city? Yeah, I guess 6,000 students. That's what it says. Literally over half. I mean, people live in Falmouth as well. Like, yeah. Slightly over exaggerated. The same still now. Figure out what one. Yeah. It's what we're doing, but I'm just saying this. Yeah. Or we could use areas, right? Yeah.
And then relating that, you got it's sort of finding material around further rapid, kind of
It's all about the that's so.
no, I think it's excommunicated, it's the total.
I'm saying, see them saying application.
You send the links in the chat, which is the volcano practical,
Volcano practical.
because it's not the volcano practical.
Okay. Oh, so that's this one. When should this start?
Yeah, no, I think that's pretty late.
Yeah, exactly. So the chat.
For everyone, people say in the Q&A that is open the chat for everyone to say that in the
Yeah,
but that is not a good idea. Yeah.
Yeah. So it's stuck like this. So they have that one. Okay. Yeah. So that's it. It's late, but yes.
So we currently Live sharing, yes. Okay.
Okay.
All right,
Bye.
great. So we're going to start the next session. Thanks, Milan. So the next bit is going to be volcano modeling. So it's learning how to interpret some of the data once you're absolutely sure it's a signal and you've got rid of all those noise sources we spent the morning talking about. There are a couple of absolute experts in modeling volcanic deformation in the room. So feel free to jump in and make contributions at any point. The first part of the practical is going to be looking at MOGI sources, and there's also some aspects in here about topographic correction and how to kind of refine it. It's a Jupyter Notebook practical like you had yesterday, and Rachel and Eliot are going to be leading this session. Take it away, Rachel.
Hello.
Susie.
Okay, so like you're familiar with Jupyter Notebook and everything. I'm Rachel. And yeah, so this is basically kind of a way of making the most of the InSAR measurements and actually like making sense of what they mean. So there's a lot of analytical models out there for kind of volcano deformation. If you make it like really simple, like the simplest you possibly can, we kind of start with something called the MOGI model, which was by someone called MOGI, and it's kind of a point source. So it's just like a little sphere almost, but it's more like it's a point source, and that represents the magma chamber, chamber beneath the surface, and you can sort of use it as an analog, and you can apply either a change in pressure or a change in volume to the point source, and that then gives you a sort of a deformation signal, and you can then use that and sort of compare it against your InSAR data and figure out what the residual is, so what, like how much difference you have left over, and that can tell you how accurate really your sort of volume or pressure measurement is. So yeah, here we've got just a bit of blurb about sort of why, or like volcano deformation. So we assume that it's to do with sort of magma movement and magma intrusion into the system, but it can also be like tectonic things happening, or like hydrothermal systems are quite important as well. So we're not looking at that today, so don't worry. Okay, so this here is the MOGI model. So as you can see, this is the point source here, and then this is the surface. Well, this kind of here is the surface, so XY conditions. And one of the main sort of criteria for using the MOGI model is that the radius of the point source is smaller than the depth. So basically, we just want to avoid this expanding to a point where it kind of comes above the surface. That's not what we want. We're doing subsurface. Yeah, and you've kind of got your conditions down here as well. It's all very nicely laid out. And this is the kind of set of equations that MOGI applied. So you get displacement in X, Y, and Z. Yeah, and then what will your parameters mean? And then this is where this is like what is used to kind of change in volume or change in pressure. So you've just got two different equations here, but they both are the MOGI model, depending on how you want to approach it. So here there's just a couple of kernels where Andrew, who wrote this script, has plotted the MOGI model, so you can run these and get some results. Oh, let me just run my entire thing. And don't know if has everyone run them and got some cool plots that look like this? Yeah, and so what you have here is the displacement, in the X direction. So you've got an expanding sort of surface. So it's kind of creating a little dome here. And this is in the X direction, the Y direction, and then this is kind of overall just magnitude from the surface. Yes, and as you like, I think it's written earlier up, this code, you can kind of have a look at the different parameters in it, and you can change some of them if you want, just to see what kind of an effect it has. So you can change, well, there's like the grid spacing, if you really want to change that, but there's the kind of the volume change and the size of the source as well. That actually has quite a big effect, unsurprisingly. Yeah, and here is sort of, these are, the arrows are the horizontal displacement, and colour is the vertical displacement. So you can see it's all coming out this way and then also moving outwards sort of on the surface. And yeah, it's just another way of sort of presenting the data. And yeah, then there's a profile along it. So you can see, again, just the different ways of visualizing what's happening is horizontal, it's always moving negatively because it's moving outwards in like the same direction. So one side is moving negatively, one side is moving positively, and then the Z displacement is doing again what we've seen, which is just sort of expanding in the middle. Yeah, so if you want to have a play around with some of the parameters in there and see what kind of an effect they have, if you want to do that now, if anyone has any questions or anything. No. Cool. Okay, and then yeah, just have a look at that, and then Eliot will come and do the second bit.
Start before we get to the second.
Yeah, we're like this bit. So I could probably add, there's a lot more like analytical models that exist that kind of complicate it more. They change the shape, or they change like kind of add bells and whistles, like in terms of melody and stuff. But the MOGI, even though it's the most simple, is like a really, really applicable model. Like it works really well for a lot of different cases. So it's the basic one that everyone will turn to, like initially, just to get a good sense of what's going on. So yeah, but there are more out there. Easy to use, less easy to use.
Just to be sure that I understood correctly, so this plant gives that it's something. It's let's say in terms of access, it's not. Of course.
But not a line of sight or something, it's just really.
No, yeah, this is it's totally synthetic. Like it's just not so the line of sight. Oh, yeah. There's no like project.
Question.
Oh no.
Sorry. Yeah.
Where is the oh yeah, sorry. Is that, can you hear me?
Yeah.
Hello, so just answering the question, where is the X center and Y center located? They're kind of, if I understand correctly, it's all the same center. So if we go back up to here, this is the center. So the X plane goes all, or the X, sorry, axis goes along here, the Y, and this is the surface plane. And so this is the center directly above the point source. Yeah, I hope that answers your question. And then the second one, what is the meaning of an isotropic half space and why decide to have this assumption? Okay, so I think the decision for the assumption is simplicity, because it's like just a very difficult thing to try and model. So yeah, you're kind of stripping it back to basics, and just you can kind of add things in later, I guess. And so this is like just the most simple one that we possibly can. An isotropic half space, basically, so isotropic is kind of the same in all directions, really. So it's like we're not saying, oh, there's like a big sort of I guess uneven levels of like pressure or like strength or mechanics like anywhere else in the system, if that makes sense. So we're just making the whole thing homogeneous so that we can get the most simple signal possible. Yeah, and a half space is essentially just a way of making, somebody might, if you want to jump in. Yeah, so right. Yeah, so it's kind of, yeah, it extends infinitely. I don't know if you had that. So I meant, where should I put? We should put for such as the summit crater or ooh. Oh, so the X center. I think it depends where you, if, okay, sorry. Hang on. Right. Okay, sorry, I was answering this question. So the X center and Y center for modeling such as the summit or the crater, I think it depends on what you're modeling and what you like, what measurements you have, because it sounds like you're thinking about sort of considering a real system, because with this we've taken, there's no topography, there's no crater, there's no mount, there's no flank, but there will be, if you're looking at a specific system and you know that there's a kind of a magma center somewhere and you want to try and apply this model to it, then you would use above where you think the signal's coming from. Yeah, basically.
Okay, I was going to answer the next guy who's asked this question in all caps.
Okay.
So the point of the exercise is that you get some familiarity with the MOGI modeling. You get some familiarity with what the different type of analytical source geometries might look like when they're projected into line of sight, because that's not something that's hugely intuitive. So what you can do with the exercise is follow the instructions in the text and change the parameters and see how, if that affects the shape of the signal. If you've got more specific questions, stick them in.
Sure. Okay. And oh. Good. Wow, that was helpful. Okay, and the next question. In the first plots in section 2, impacts of satellite line of sight. Okay, so we're going to move on to the section 2 in a second, so don't worry too much about that. I'm sure that Eliot will answer all of your questions. Yeah, okay, and you're welcome, Eamon. I'm glad that helped. Okay, I think we're all done there for now. Oh. Okay. Okay, thank you. Yeah, Pedro's going to share the link for you. Okay, so the next question, the indicators to evaluate MOGI performance. So this will actually be covered in the next bit a little bit as well. So when you're comparing your results, like your InSAR results with the MOGI results, you'll sort of do kind of essentially take one away from the other as a surface plot. So you'll have a leftover like residual. So how much is left over in kind of each little area of the plot, and that overall will tell you kind of the bigger the value, the bigger the difference, then the less well the MOGI model has performed against your results. Yeah, so you kind of want to get the lowest variation possible across the board. Oh,
Yeah.
how come? Okay, so oh my god. So the change in volume, how can the change in volume be interpreted in the model? So if I'm going to assume that you mean, what does the change in volume mean in the model? And if so, then that's an addition or kind of removal of magma into the body, into the source here. And yeah, you can kind of convert the change in volume to the change in pressure if you want. But yeah, I guess it depends on the properties of the magma that you want. So yeah, the change in volume could, I mean, realistically speaking, no, because the MOGI model is for, well, what we're applying it to here is a magma chamber. So something weird would happen if you added water to it. But in terms of volume, yes, it could be anything because it's just a volume. It doesn't actually take into account any other parameters of what you're adding. It doesn't have like density, viscosity, I don't know, chemical compounds, anything like that. Like it's irrelevant what it is because it's assuming that it's non-reactive, it's incompressible. So yeah, it's just a fluid that's gone in. I hope that answers your question. Yeah. Does anyone in the room have any questions? Oh, okay. Right. Thank you. Cool. Right. Well, Eliot's going to take over now with your line of sight and InSAR and stuff. Enjoy.
Cool. So we're now going to move on to, we've plotted our displacements in the different direction fields, and we're now going to see how the influence of the line of sight of the satellite, which hopefully you've learnt about and you're all experts on after the last couple of days, and how that may influence what the displacement looks like. So we've gone from having a radially symmetric source, and we're now going to see that once we've got this radially symmetric source, once we're looking at it from the side angle and from space, these things that are caused by something that's radially symmetric, so the same in all directions, suddenly doesn't look that way because of the angle that we're looking at it from the, well, from the satellite. So as, well, quick recap, I'm sure you've done it lots over the last few days. Satellites can be in ascending or descending, but in this imaginary world that we're in, we can change our heading to whatever we want it to be. So in this first section, what I'd like you to do is have a play around with different headings and incidence angles and see as our satellite is going in a different direction around the Earth, how that will impact our line of sight. So our heading is relative to north, which direction we're going. And our incidence angle is what angle we hit the ground at, okay? So play around with these and have a look at how that will, if I press run, how that will change your relative contributions of the X component to line of sight, the Y component to line of sight, the Z component to line of sight, and then our total line of sight, okay? So each individual component will add up differently. And if we change our incidence angle and our heading, those components will add up in a different way. And what I think is really worth taking away is if you have a look at this total displacement field, how weird it can look relative to your initial radially symmetric source. Okay, so if you have a run through that box, and then we'll go through the next bit after that. What might be worthwhile doing as well is if you copy a cell, so you've got a copy of the original, and then make a new cell, and then when you break it, you've still got your old one. Yeah, so for this first one, yeah, the metadata for your SAR product will tell you the incidence angle. What is the best length of data as input? Is it sufficient if only before and after? So, that's quite a specific question. So I guess it depends on your coherence and when you expect the deformation to have taken place. In lots of eruptions, you may get deformation before the eruption, but not all of them. And in some eruptions, you will get deformation afterwards. But if you have an eruption that changes the ground surface massively, then you may not expect coherence anymore, so you wouldn't be able to use InSAR. Pedro, could you share the Jupyter notebooks with us? People in the room, have we had a play with our line of sights? So to exaggerate the point, if we take, I'll keep the heading at -10. If we change our incidence angle to 90, oh, they're not numbers.
Alt shift. We change the keyboard.
Shift.
Alt F.
Sorry.
There you go.
Okay, thank you. Yeah, perfect. Okay. So that's quite right. Okay, so we've changed our incidence angle to completely vertical. So now it's just coming directly down. And you can see that we've got no sensitivity to X or Y component. Okay, so depending on our angle of incidence gives us different sensitivities to different directions of travel. And as our satellites are going around the Earth in the north-south or south-north direction-ish, it gives us very little sensitivity to the northward component. So you'll see that if we change back to our original, which I think was 36, then see how the axis on the X direction, the displacement's much larger than the axis in the north-south direction. So for our line of sight, our north-south is having much less contribution to the actual line of sight. Okay, cool. So now we're going to move away from just the magnitude to actually wrapped line of sight. So as I'm sure you've learned over the last few days, or hopefully, is that we measure these changes in the unit of wavelength. So or they're plotted in wavelength if they're not doing the total displacement. So if we set our wavelength as, I can't remember. Well, here we've used 10 mil fringes. So every 10 mil would be a new wavelength. And we can see we now get our line of sight in a different, well, it's just plotted differently, but it exaggerates this point of our radially symmetric source is now looking very different once we're in line of sight. Okay. So then we're going to move on to the effect of topography. Is everyone in the room happy? Yeah? Okay, cool. So at the minute we've been using our elastic half space, which is essentially a flat surface. But in reality, and especially at volcanoes, the topography varies quite a lot. And Williams and Wadge provided a kind of first order approximation for modifying our analytical solution to include topography. So for more complex scenarios, you'd use finite element modeling. but for now it does a pretty good job. So if you want to work through this next stage where we're going to have a look at how the topography influence our deformation measurement. So this is all moving away from why our simple analytical model that looks radially symmetric looks very different once we're actually interpreting data. Cool. So if you work through that section too, and stop before you get to the real world example. Incidence angle of 0 is not producing InSAR. Cool. I'll scroll up. So we're going to change our. So incidence angle of 0 is not producing InSAR. You might have to be a bit more specific with that question, but yes, you're right. InSAR satellites don't have an incidence angle of 0, but we're just showing how the incidence angle, the variation in incidence angle will change your measurement. Name error. I'm not sure about how to solve the Python problem. Maybe you could just try refreshing and logging in again. From the question from earlier that we said we were going to answer now. So it may look like there's subsidence, but there is no subsidence. It's just that the ground is moving away from the satellite rather than towards the satellite. So once we're in line of sight, the relative contribution of each is different. So we're no longer just looking at our simple model where the ground's moving outwards in every direction. We're now looking at whether the ground's moving towards or away from the satellite. So just because the ground's moving away from the satellite doesn't mean it's subsiding, which can be hard to get your head around. Or not so hard if it depends. Yeah. People in the room, more time, done, happy? One more question. Find the optimal solution. How to find the optimal solution? Well, that's an inverse problem, which you should be able to solve, but basically by minimizing the residual error for what you're trying to fit. It's quite satisfying ticking them off. Okay, cool. So for the real world example, I'll leave you guys to run through this by yourself. But essentially what we're going to do is look at an example data set from the LiCS portal. We are going to load the DEM, or we may have already loaded the DEM for that model. And we're then going to try find the best fitting MOGI model for this data. You can play around with different parameters to try find the best fit. And then, I don't know, if you want to, you can have a competition between yourselves to see who's got the lowest residual, and you can be charged, you can be the MOGI king of the, or queen of the session. I wouldn't change the Poisson's ratio or the Poisson's ratio is a ground property that determines how much the ground deforms in the perpendicular direction if you apply a force in one direction. It lets you know how much displacement, how much the ground deforms in a different direction, basically. But don't change that.
For the last cell, is this an ascending and descending track that we're looking at? We've got model, observe, and residual. And I assume it's for ascending and descending.
I'll quickly run the cells and just have a look.
Yeah, these figures here.
Yep.
The top ones are.
Yeah, so see the track names on the left.
Yeah, that's what I was looking at.
The A, yeah, ascending and descending.
Okay.
And then if you go on the portal for this volcano, you'll also have the metadata there too. No worries. So here we can see the effect of our ascending and descending track and how you'll get different displacement fields in each, and how actually using them together can be informative too. I don't actually know the right answer for the bottom bit, so I can't tell you who's right or not, unfortunately. Yeah, exactly. Yeah, that's true. How do we know the best choice for the parameters? So the best choice for the parameters are the ones that minimize the residual. So you're trying to minimize the residual. So the residual is the difference between the model and the data. So the best choice is two things. It's a model that's realistic. So if you're saying that your magma chamber is super shallow but super big, or super deep but super small, or you might be suggesting that there's so it's realistic to the volcano setting and then minimizing the residual. So quickly run through. This plot's slightly unusual. The areas with the lowest coherence are the brightest pixels. But you can see that we've got low coherence over the highest topography. And then that means we have no data in this portion of the model. So it means that when we come to modeling this data, we're not trying to match anything that we've masked out, basically. And we're only trying to match the pixels that we've deemed of a sufficient coherence to model. And then we can play around with our different cross sections. So if the more you play around with the volcano portal, you realize that for lots of volcanoes that may be in tropical regions or have ice cover, this coherence can actually be a very, very significant problem. But for this example, it's good. Okay, how are people getting on? Has anyone written an inverse problem to minimize the residual and they've looped through all the parameters? No. Okay. I'll leave it there. I think it's worth mentioning that we've chosen the Mogi model. That's a spherical cavity. But in reality, there's lots of other options for what we can use as source models. And also we can use finite element models, numerical models that don't rely on simplified solutions. But it's worth remembering that for us to inverse the problem, a lot of the time we do depend on these analytical models and how they all have different contributions once you've moved them into line of sight. So I don't have anything else to say, but you keep playing around with the software, and then if not, you can have a quick break before the next talk.